Hi everybody, in this video I'm going to go over Apex Study Section 7.1.1. So we're starting Unit 7, which is about energy and matter. And a lot of this we actually already discussed at the very beginning of the year. So the first part of this will be a review. So at the beginning of the year we said that all atoms and molecules are in motion. They're always moving. And this is the same thing that kinetic theory says. So kinetic theory just says that all atoms and molecules have kinetic energy. Kinetic energy is the energy of motion. And that just means that all atoms and molecules are in motion, okay? And we know from the beginning of the year that the phases or states of matter are solid, liquid, and gas. And each phase or state of matter has a different energy of motion, right? So solid, we said they are still moving. Remember we said these little wiggle marks or vibration marks. They're vibrating in place. Liquids are moving a little bit more. So we used to draw tiny arrows to represent that. And then gases, of course, are moving the most. So as we go from solid to liquid to gas, we increase our kinetic energy. And that just means that we are increasing the motion. Okay? And we know that there are these phase changes. So if you go from solid to liquid, we call that melting. As we go from liquid to gas, we call that evaporating. If you went from gas to liquid the other way, we would call this condensing. And from liquid to solid is freezing. Okay, so we remember that. We also talked a little bit before about pressure. Pressure comes from gas molecules colliding with the walls of the container. So we know that gas molecules move the most, right? So they're moving around in their container. Let's say we put a lid on this container so they can't get out. And they're bouncing around, and some of them will collide with the walls. And when they collide with the walls of the container, that creates pressure. So if we're at our normal sea level, like where we are at now, this is the case here. But if you go up to a higher elevation, let's say now we're on the top of a mountain. At the top of the mountain, there is less gravity pulling down on these particles. And as a result, the particles can move up more, right? So we're here, this is lower elevation. Okay, and most of our particles are stuck at that bottom. They're still moving around and colliding, but they're stuck at the bottom of the container. If we're at a higher elevation, there's less gravity, so they're moving higher up, okay? And that means that they're going to have more collisions at this lower elevation where they're stuck on the bottom than at a higher elevation when they can move more freely. So at a lower elevation, you get a higher pressure. And at a higher elevation, you get a lower pressure. And that's why if you live somewhere like Denver, you live up at a high altitude, it will actually take you longer to cook things like boil an egg because you have a lower air pressure. And that's because there's less gravity up there. All right, so let's move on to something new. What we haven't talked about yet is phase diagrams. So this here is an example of a phase diagram. Now, we all know that the phase of matter is determined by the temperature, right? If something is hotter, it's more likely to be a gas. If it's colder, it's likely to be a solid. However, it also depends on the atmospheric pressure. So a phase diagram shows you what phase matter is in a given temperature and pressure, okay? So let's say, for example, we want to figure out what the state of matter is at 0 degrees Celsius and 0.5 atmospheres of pressure. So what we would do is we would draw our line here. Okay, so this is from 0 going up. And now let's say 1 atmosphere of pressure. Okay. And we see here where they cross is the state of matter. So at 0 degrees Celsius and 1 atmosphere of pressure, water is a liquid. All right, let's do another one. Okay, let's say we want 0.25 atmospheres of pressure and 100 degrees Celsius. So again, we draw our straight line up from our gas and our line over from our pressure here. And we can see that at 100 degrees Celsius and 0.25 atmospheres of pressure, this is a gas. Okay, so this is how you determine, if you're given a pressure and a temperature, what state of matter something is in. Now, I want to notice some things here. If we have 1 atmosphere of pressure, right, this is the point where it goes from solid to liquid. And so this, when we have something solid and it goes to a liquid, we call that the melting point. It's the temperature at which it melts. And then here, where we cross from liquid into gas, when something goes from liquid to gas, that's evaporating, and we call that the boiling point. Okay, so this is the melting point of water, and this is the boiling point for 1 atmosphere. Now, we can do the same thing for 0.5 atmospheres, and this would be the melting point, and this would be the boiling point. And you can see that they're different. So at 1 atmosphere, the melting point is actually a lower temperature for a higher pressure. So this 1 atmosphere is a higher pressure and it has a lower temperature melting point. Then if we look at the boiling point, at our higher pressure here, we're at a higher temperature. Okay, so at a higher pressure, you have a higher temperature boiling point, but you have a lower temperature melting point. And this is for water. Okay, so we should be able to read these phase diagrams fairly simply. Okay, I also want to point out here that phase diagrams are different for different materials. So this is carbon dioxide and this is water. And if you look at these, you can see this difference here, that water, the line between liquid and solid slopes backwards, right? And for carbon dioxide, it slopes forwards. Okay? And what that means is that in carbon dioxide, you can have something that's a gas and then it turns to a liquid. And then if you keep increasing the pressure, it will turn to a solid. But that won't be the case in water. In water, if you have a gas, if you increase the pressure, doesn't matter how much you increase it, it's never going to become a solid. Okay? Because of that backward slope there. So most molecules look like carbon dioxide. They have phase diagrams where the solid to liquid line is sloping forward, but water is a special case where it's sloping backwards. Okay. All right. Now, let's relate this to intermolecular forces, which is what we talked about last time. If you are going to melt or boil something, you need to weaken or break intermolecular forces. So intermolecular forces need to be weakened or broken for a substance to melt or boil. And if they have stronger intermolecular forces, it's going to have a higher melting and boiling point. So let's look at water. Okay. Okay, if this is solid water, then we have this intermolecular force between the hydrogen and the oxygen. And this is a pretty strong intermolecular force. I'm writing IMF as the abbreviation for intermolecular force. Okay? Now, if we have a liquid, we know the water molecule is going to look the same, but they're going to be further apart. Okay, So we still have this interaction between the hydrogen and the oxygen, but this is a weaker intermolecular force, right? Because they're further away, it can't be as strong. So this is the liquid state and has a weaker intermolecular force, okay? And then last would be our gaseous state. And again, our molecules look the same, but they're even further apart. So at this point, when they're a gas, there is no longer an intermolecular force. They are so far away that they're not even interacting anymore, okay? So this means that here, if we're going from solid to liquid, if we're trying to melt something, then we need to go from having a strong intermolecular force to a weaker intermolecular force. So this needs to weaken our intermolecular force. If you go from a liquid to a gas, you go from a weak intermolecular force to no intermolecular force. So you need to break the intermolecular force, okay? And this is the case from liquid to gas, which is boiling, okay? So in order for something to melt or boil, you need to weaken these intermolecular forces. As a result, if you have a stronger intermolecular force, you are going to have a higher melting point and boiling point. So for example, if you have something with strong intermolecular forces like water, it's going to take more energy to break those apart to melt or boil it. But if you have something with only weak intermolecular forces to begin with, like nitrogen, it's not going to take that much energy to break them apart. So it's going to have a lower melting and boiling point. And we can use this to make some predictions about what the melting and boiling points of different molecules will be. So let's do some examples here. Okay, we have CHCl3. So these are our H's here. This is our Cl. Okay. And we know carbon, hydrogen, and chlorine, they're going to be far apart from each other on the periodic table. So this is going to be a polar bond. Chlorine is more electronegative, so it's going to have that partial negative. It's going to pull the electrons towards itself. The hydrogens are going to have a partial positive charge. So we know this is a polar molecule. Since it's a polar molecule, it has dipole-dipole forces, okay? It does not have hydrogen bonding because hydrogen needs to be bonded to nitrogen, oxygen, or fluorine in order for it to be hydrogen bonding. So it does not have hydrogen bonding. It does have van der Waals forces. Remember, that's just from the electrons clumping on one side or the other. So you always put the strongest one, which is this dipole-dipole, and then any weaker ones as well. All right, let's look at NH3. So here we have nitrogen and hydrogen have very different electronegativities. Nitrogen is going to be partially negative, hydrogen is partially positive. Okay, so this is a polar molecule. And we have nitrogen bonded to hydrogen. So we have hydrogen bonding. And then we have everything weaker than that too. So we also have dipole-dipole because it's polar. And we also have van der Waals because everything can have van der Waals. Okay? All right, so let's look at our last one here. This is CS2, carbon's in the middle, sulfur on the other side. So carbon and sulfur do have different electronegativities. So this bond is polar. However, this is a linear molecule, so it is symmetric. And since it's symmetric, it is a non-polar molecule. This is a case where it's a polar bond. Carbon and sulfur have different electronegativities, but it is a non-polar molecule because it is symmetric. And if you are non-polar, you can't have dipole-dipole, you can't have hydrogen bonding, so the only thing you have is van der Waals. Okay, so let's compare these. Hydrogen bonding we know is the strongest. So NH3 is the only one with hydrogen bonding. So this has the strongest IMF. Okay. Then this one here has dipole-dipole and van der Waals. Okay. So dipole-dipole is not as strong as hydrogen, but it's the second strongest. So this is sort of the middle intermolecular forces. And then CS2, it only has van der Waals. Okay. And those are the weakest. So this has the weakest intermolecular force. Okay. So we said if you have stronger IMF, you have higher melting and boiling point. Okay, so that means here, NH3 has the strongest intermolecular force, so this has the highest boiling and melting point. Okay, this is middle intermolecular force, so it's going to have the middle boiling or melting point. And this is the weakest intermolecular force for CS2, so it's going to have the lowest boiling or melting point. Okay, so this one's going to boil at a low temperature. That means it might even be a gas at room temperature or a liquid. This is going to boil at a very high temperature. That means it's probably going to be a solid or a liquid. Okay. So from today, we need to be able to understand what solids, liquids, and gases are, that they're all in motion. We need to know where pressure comes from. We need to be able to interpret phase diagrams. We need to understand why stronger intermolecular forces means you're going to have higher melting and boiling points. And we need to be able to use that to predict the type of intermolecular force and use that to make predictions about melting and boiling points. Thank you.